Hey, how you doing? My name's Elton, and welcome to Learn Docker in a Month of Lunches. This is episode 6, where we're going to be looking at running multi-container applications using Docker Compose. So we're into the second stage of the learning journey here. So part 1, the first 5 episodes, the first 5 chapters of the book, we're really getting you down with the basics. So containers, images, registries, and storage, so you can understand like how the container environment gets put together for you by Docker. We didn't cover all the stuff in a whole ton of detail. So, the Docker file syntax, there's more to that. The container commands, the image commands, there's a lot more to that stuff, but that will unfold as we go further on into the book. And the second stage of the journey, which starts today, is looking at multi-container apps and how other parts of the Docker ecosystem help you to run distributed applications across several containers. Okay, so let's push this button here and we'll go on to the slides. So usual format, if you haven't seen the series before, we start with a quick look at the homepage for the book with any updates that I've been through. Then the focus is a single chapter. Today it's chapter 7 because we've got the N+1 issue with the chapter number and the episode number. And then we've got some Q&A. So if you've got any questions about the stuff I go through today, put it in the YouTube chat or put it in the Slack channel, which there's a link to that from the DIAMOL.net website. And then towards the end of the session today, I'll check through the comments. If there's anything that we can spend some time talking about, I'll go through some of that stuff as well. Okay, so let's flip over to the homepage for the site. So this is diamol.net, Docker in a month of lunches, Diamol. So today, if you haven't got a copy of the book yet, if you want and you're watching live, today the books are half price. Everything on Manning is half price. You can go and get the digital book or the print book for 50% off. And then with the money you save, you can also go and buy a copy of Learn Kubernetes in a month of lunches, which you can shelve until next year when I do the live stream for that one. If you're not watching live, and I forgot to add this before, I've got a 40% off code. So anytime you watch this, you can put this Stoneman PC into the offer code in the Manning website, and you'll get 40% off your basket. I've been keeping this up to date with the stuff I've been talking about. So we've got the first 5 episodes there. If you missed any of those, as soon as the stream finishes, they're up on YouTube, so you can watch them again. So that's what we covered last week. And then we're here with week 2. We're running multi-container apps with Docker Compose. Okay, and that's kind of it for the blurb. So I'm going to switch over to the chapter. So we've been through part 1, understanding Docker containers and images. And then part 2, things step up a little bit in part 2. The great thing about Docker is that if you focus on these kind of small individual topics, you can build up a lot of complexity over just a short amount of time. So today we're going to look at Docker Compose, but by the end of the week, we're going to have done things like working out how to make your apps reliable when they run across distributed containers with health checks. We're going to look at observability using Prometheus, which is a way of monitoring your applications. We're going to look at how you can run several environments on a single machine using Docker Compose. And at the end of the week, we're going to end with like a CI service where you're using Docker Compose to build and test your application. So there's a whole chunk of stuff we can get through this week. Okay, but let's get started. So, chapter 7, running multi-container apps with Docker Compose. Docker Compose is a separate part of the Docker ecosystem. So you have the Docker file to package up your images and the Docker command line to work with containers and images. Docker Compose is a separate but related tool that manages several containers for you. And it's for the scenario, which is the common scenario, where, as it says here, most apps don't run in a single component. Like even if you've got an old monolithic app, chances are really it's an n-tier application with a couple of separate layers, which may or may not be physically distributed. You can run all those things in separate containers, and Docker Compose lets you structure what that application looks like with all those different containers and how they fit in together, and also manage the application. So there's kind of 2 parts to what Compose does. So if you remember back in the episode where we looked at this NASA astronomy picture of the day application, when we were looking at multi-stage Docker files, to test the application, what I had to do, and the exercises kind of guided you through all this, I created a Docker network so the containers could plug into that network and talk to each other. And then I started up the containers individually. There's like an API to fetch the data for the current day's image. There's an API to log access requests, and then there's the website itself. I had to start all of those containers using the Docker container run command. And I had to make sure I got all the parameters correct. So, the ports that I'm publishing, make sure they plug them into the right network, all that sort of stuff. As your container applications get more advanced with volumes and mounts and all that sort of stuff, the container commands become more and more verbose, and it becomes brittle to try and manage your applications like that. So what Docker Compose does is, and I'm going off the script here, Docker Compose is a file, it's a different file structure, and it defines the desired state of your application. So rather than imperatively saying to Docker with the Docker command line, Docker run this container, Docker run that container, Docker create this network, what you do is you declaratively describe the desired state. So I say, I want to have a network called this, I want to have a container called this, which plugs into the network, and another container called this, which plugs into the network. And then you have this compose file, which describes the structure of your application. And then the Docker compose command line makes that desired state reality. So every time you use the Docker command line to deploy your application, rather than explicitly removing and starting containers, Compose does that for you. You say, I want all this stuff, and Compose says, well, this is what's currently running. I'm not running the web container, so I need to start that, or there is no network, so I need to create that. And Docker Compose works out from where you currently are to the desired state for you. Okay, so it's a pretty simple format. It's a different structure to the Docker file, so it uses YAML, which is, you need to learn YAML if you want to get into the container world, because Docker Compose, Docker Swarm, and Kubernetes, they're all based on YAML. So here's a simple example. I'm going to switch to the code view, because that's going to be a bit easier to read. So let me open this. We're in chapter 7 exercises. The first one is to-do list. And this is what it looks like. I'll zoom up a little bit. So it's YAML, so indentation is important. Each time you indent, that's a different layer of the definition. It starts with a version number. So Docker Compose has been through lots of versions. Some added features, some took away features. So this tells the tool which version of the schema you're working on. And then we have this stanza of services. Now, Docker Compose will ultimately create containers for you, but when you define your application, you work at a higher level. You work at the idea of services. And a service could be run as one or more containers. And we'll see during the episode that I can define a service. And when I run it, it'll just be a single container, but I can scale up and run multiple copies of the same container application as part of the service. Now, within the service, I'm going to define all the bits of my application. So I've got this thing called to-do web, which will be the web application for the to-do list that we've seen previously. And inside here, I've got pretty much all the things that I would put into my Docker container run command. So this is the image that I want to run the container from. These are the ports that I want to publish. So again, I've got the host port comes first, and then the container port. So I'm listening on port 8020 on my host, and that will send traffic into port 80 on the container. And I'm plugging into this network called AppNet. And then the network is defined in a separate stanza here. And I'm saying that I'm expecting this network to already exist. So Compose can create these things for you, or you can say, look, this is a network that I've already created. So leave that one and use it as it currently is. You can also include volumes in here. So I can have my whole application structure defined with all the containers, the networks, the volumes, and everything in one place. It's a nice, concise way of describing your entire application. So this is what I'm saying in here. It's kind of human readable. YAML's got popular because it's easily to convert into JSON. So if I've got a YAML file, it's easy for me to read as a human. But if I want to send it to an API, it's pretty trivial to convert it to JSON, and then the API can understand it too. So I've been through all these pieces here. So the version flag, Docker Compose will eventually lose the version because there's a desire from the Docker team to not have these magic numbers in there, given that Compose can work it out itself. So that will probably go away at some point. Services are all the components, and then networks are how the things get joined together. So if I was to run this app, it would be pretty much equivalent. That compose file that we've just seen is almost the same as the Docker container run command that you can see there. So the -p flag is publishing the ports, and they're all defined in the compose file. The name of the container, the name you use for the service, that becomes a part of the container name, and that's how containers find each other over the network using that container name. The network I'm connecting to, and then the image that I want to run. So I think now we're going to go and actually do that. The other advantage of the compose file, it's like this, it's the documentation of your deployment, really. So your Docker file for your each component is the documentation for how you package up that component, and the compose file is the documentation for how the whole thing runs. And it's a really nice way to work with it because A, it's a known format, so I can use a little tool to generate me a little diagram, which is what I've got here. And B, it's never going to be out of date. The compose file lives inside your source code, just like your Docker file does. So, and your compose file is what you're going to use when you're testing locally. You'll maybe use it in your CI server. So it will always be up to date and working correctly. It won't get out of date and stale like static documentation does. Okay, cool. So the syntax is slightly different when you're working with Docker Compose. So I'm going to open my terminal here. I'm going to create this network. Docker, if you're running on Docker on Windows, it creates this default network called NAT. And in earlier versions of Docker on Windows, you could only have one network. So that's why we create this network called NAT, even if you're running on Linux. I'm using Linux containers, but to make the exercises work cross-platform, I make sure everyone uses that same network, and we call it NAT. I'm in the folder for my application for all the DIAMOL source code. So if I browse in here, I should see my I should see if you can read that, which obviously you can't. So let's clear this down. There's my Docker Compose file that I've just looked at, and that's the PNG. That's the graphic of the architecture that we've just looked at. Okay, so the compose syntax is slightly different. So because it's a desired state thing, you don't use commands like run and start for individual containers. You tell Docker Compose to start up the entire application. That's what the up command does. So I need to be in the folder where the compose YAML file is, because that tells Docker Compose what to do. And then I'm doing Docker Compose up. And by convention, it expects to find a file called dockercompose.yaml. And then when it finds that, it'll do everything that it needs to do. So what we're seeing is here, these are the logs coming out of my to-do web application. And we can see right at the beginning here, if you can see that over my head, Docker Compose says it's creating the to-do list web. It's attaching to it because I'm not running in detach mode. So remember way back in episode 1, you can either run a container interactively where you see the output in your shell, or you can run it detached where the logs just need to be collected by Docker. This is interactive, so I'm seeing this attached to my shell. Okay, so let's zoom this down a little bit so we can actually see what's happening now. So you may or may not already have that NAT network if you've been following through the exercises, in which case you'll get an error message saying it already exists, but that's fine. You just carry on. And now this is the output that we're seeing already. So we've got the logs from this one web application. There's just a single component in this compose file, but it's still useful to document everything in a compose file. It means I don't need to have a README document that says, in dev mode, we use port 80 and we connect to a network called NAT. That's all effectively documented in the compose file in a way that's actionable. So anyone who just does Docker Compose up, all the little bits and tweaks of the parameters are all concrete inside that compose file. Okay, so if I browse to the published port, which is localhost 8020, if I go up here, oh, I didn't actually copy that in, did I? But I should have it in my list. 8020. There we go. Okay, so this is a brand new instance of the container. So there's no data in there like we saw in the previous episode. Data dies when the container gets removed. So I cleared everything down before I started today's session. I did pre-pull the images because there's no point watching me download images. But so when you do this for the first time yourself, Docker Compose will also download the image if it needs it and then start the container up. So you might see the pulling the image layers first before you get into the application, but the output will be the same. The app will behave in the same way, and it'll be the same as when we used it in a previous episode. But now we've got this compose file, single file that defines the whole structure of the application. Okay, cool. So the compose format records all these kind of top level resources. So these things that are first class citizens in Docker, like volumes, secrets that will come to, and networks, then Compose can manage all those for you. And this having this single application defined in my Compose file, well, it's useful for capturing all those things, but Compose is really good when you start working with multi-container applications. So we're going to now switch over to a more interesting Compose file, which is from that NASA astronomy photo of the day application. So the image of the day Compose file, it's the same structure, it's the same format, so it's going to be very familiar even if you've just seen that previous Compose file, if that's the only one you've ever seen. Starts with a version number and then a list of services. So these are indented, so these are all separate services. They'll all run in different containers. So my access log is the Node.js application that records how many people are using the application. And then my IOTD is the actual API, which goes and fetches from NASA and it caches from NASA. It goes to faces from NASA's API and caches the results so we don't keep pinging their API. That's the Java application. And then we keep going down here. We've got the image gallery itself, which is the web UI that talks to those two APIs. That's not very good. Talks to those two APIs. This is the only one that publishes a port. So we've got the image is the image gallery application image that we used in chapter 4. They all plug into the same network. This one's got an extra stanza in here. This says it depends on the other two applications. So with Docker Compose, you can map out the spec of your application, including these dependencies. So the web application can only function if the API is already up and running because it needs that to do any work. And it also expects that access log component to be running because it posts data there every time someone browses to the application. So those are dependencies that I can capture in this structure so that Docker Compose knows it needs to start those two components first before it starts my web component. They all plug into the same network. There is, let me have a look here. So the access log, I'm not publishing any ports because that's only used internally. So it's only used by the image gallery application. The API, I'm publishing a port, but I'm only specifying one number. So like I said, we've covered some of the basics of running containers, but we haven't gone into a lot of the nuances. When you publish a port, you can use the kind of two port notation that says, I'm listening on port X and I want to forward data into port Y. If you only include one port, then Docker will map that to a random port. So this is saying that the container listens on port 80 and just map it to some random port on the host. And then I could find out which port I'm using if I wanted to send traffic in. So it's a more dynamic way. If I want to publish a port, but I don't care what it is, I can let Docker manage that for me and it will choose the next available port. Okay, so similar structure, a whole list of services. Each one of those will run in its own container. And again, really all I'm doing is capturing the Docker container run statement in a declarative way, in a way that then Docker Compose can go and make the changes for me and create what it needs to create to get my application running. Okay, cool. So there's a few different configuration sections in there. There's the dependency bit that I talked about. So Docker Compose will make sure that it starts them up in the order necessary to achieve all my dependencies. Okay, cool. So I've got my little image there again, which was generated by a tool. There's a link here to that tool. It's a really great tool, little tiny, I think it's a Python app up on GitHub, and you just run this one command. It runs inside a container. You point it to your Docker Compose file, and it generates this ping, which is like a nice, handy way. You can include that as part of your CI build. And then you've got a nice architecture diagram that requires no effort, which is nice to have. Okay, so let's go and we're going to exit out of this. So when I exit from Docker Compose, and let's bring this down so you can see it, I just did Control-C to exit from the Docker Compose command that I was running. It stops my application container and it removes it. So it's kind of clearing it down for me. And now if I want to go and look at my image of the day application, I'm going to go up a level to my exercises. And this is where I've got the compose file that we've just walked through with the 3 separate components, all plugging into the same network so they can all reach each other. The underlying concepts, the network that I'm using, the containers talking to each other, it all operates in the same way as it did in episode 3 when we built those containers and ran them individually. But we're going up a level in how we define these things, and we're abstracting the container definition into this service definition and letting another tool manage it for us. Okay, so I've got my compose file there. So again, I need to be in the folder where my compose file is, or tell Docker Compose which file I'm using, and then I can use Docker Compose up. And again, with the detach flag, so a lot of the Docker Compose command lines and flags are similar to their equivalents for the Docker commands. Detach is going to put all my containers in the background and then return my terminal to me so I can see what's going on. So Compose tells me what it's doing. It's creating the access log. It creates the image of the day. And only when those two are created does it create the actual web API. So that's my dependency map in action there. So Compose has made sure that the dependent services are created before the one that uses them. Okay, so that's everything up and running. It's much simpler than doing all those Docker container commands with the brittle necessity to put in all the right parameters. All that's captured for me in the Compose file. Okay, cool. So am I going to browse to this? I was thinking I was going to browse to it. Yeah, 8010. Okay, so let's go and look at port 8010. So this previous website, this to-do application, that's died now because I killed the container, so that's no longer there. If I switch to port 8010, we'll see the astronomy picture of the day app. And this is the Milky Way over St. Michael's. That's nice, isn't it? So St. Michael's Mount is in Cornwall, which is near in England, which is near where I was brought up. So that's nice. I'll take that as a good omen for book sales. Okay, so that's up and running. So that now Docker Compose has looked at my compose file to see what my desired state was, and then it looked at what was currently running in the Docker engine. So Docker Compose is another client of the Docker API. So if you remember way back in episode 1, we talked about the Docker command line. All it does is send requests to the Docker API, which is part of the Docker engine. So the Docker command line is just a client of the API. Compose is another client of the API. So what it does is it looks at your compose file, it talks to the Docker API and says, is this container running? Is that container running? What's the spec of those containers? Do I need to create new things or replace existing things to get from where you currently are to the desired state that's in the compose file? Okay, so I've got this clear definition in my compose file. Everything works in the same way. It's all really nice and easy. And then compose can let me do some other stuff too. So I can scale up my container now. If I wanted to do this with Docker container commands, if I want to run several instances of my API, well, that's a stateless component. I can just spin up more and more containers, but I'd have to manually kind of give them different names and connect them to the network and do all that sort of stuff. But because it's in Docker Compose, I can tell Docker Compose that I want to bring my application up. So up dash D is going to be the same as bringing it up with a detach flag, but I'm overriding some of the parameters inside the compose file. So by default, everything runs with a scale of 1. So I've got a single container running each of the services that are defined in the compose file. If I specify a scale, then I can override that. So I'm saying bring everything up as defined in the compose file, but the IOTD, which is the API, the Java API, I want that to have a scale of 3. So by the end of this command, I want there to be 3 instances, 3 containers, all running the same image, or effectively with the exact same specification, but so the website can load balance between any one of those containers that's running the API. So if I run this, what we'll see is, let's make this a little bit bigger, we'll see that the access log is up to date. So Docker Compose has seen the definition for that component, that service, and sees it's already running inside Docker with a match for the specification, so it leaves it as it is. It's going to start image of the day 1 while it's already running, so it's just going to say it's going to start it, and it's creating 2 more. So image of the day 2 and image of the day 3 are effectively clones of that same container definition. So I've got 3 different containers all running from the exact same spec. And then image gallery 1 is up to date, so it doesn't touch the web API, the web UI either. So all it's done is added 2 more containers to scale up my API component. But as part of that, it looked at everything that was running and made sure everything was up to date in line with the spec in the compose file. Okay, so now I've got this. If I go and refresh the web page, so I'll go back over here, I'm getting the same output, but what we'll see is that there should be a bit of a delay each time I do a refresh, because sometimes the call from the web component will go to a new instance of the Java API. And so the first time I did a refresh, there was a little delay while it went and fetched the data and then cached it. So now by the time there's a little delay there as well. So by now it should have hit all of the API containers. What Docker is doing is that the web component is making a call into my API component, and Docker is load balancing it for me. So it's sending the request to different API containers, and we'll have a look in a second just how it does that. Okay, so if I go and look at my logs, so let me clear this down. I can use Docker Compose to look at the logs for, I don't know whether that's there or not, because it's got pasted with a white font, which is kind of fun. So I can use Docker Compose to look at the logs rather than the standard Docker container command. I could do Docker container ls and get the name of the container and then do Docker container logs. But if I'm using Compose and I'm running at scale, then I can get all the logs from all the containers from my service. So I'm saying this is the IOTD service, the API. Get me all the logs from each container. But the tail option says just get me the last log entry for each container. So what I'll see here is we get nice color coding. So for each of these containers that are running IOTD 1, 2, and 3, I'm getting some data back. And we'll see that this one fetched the new data from NASA, and that was at 1919. And then the more recent ones at 1921 and 1922. So they've all running the same. Actually, the IOTD image of the day 2 application, this container hasn't received any requests yet. So the last log entry is that the application started. So far, the load balancing has only hit 1 and 3, which is good because we can see that they're behaving in different ways, even though it's the same application in each container. It's just a question of whether they've received any requests yet. Okay, cool. So that just gets everything up and running. And we can see that well, if I browse down here, you'll see what happened here. Similar thing, actually, when I did this example to get the screenshot for the book. In this case, same again. Image of the day 2 hadn't received any requests by this point, but 3 and 1 had. Okay, so we can manage this application with Compose as well. We can't just like start it and then have to go back to the ordinary Docker commands. There are various other Docker Compose commands that we can use to work with the application as a whole, rather than managing the individual containers and trying to keep everything in check. So if I want to stop the whole thing, and again, I need to be in the same folder where the Docker Compose YAML file is, because all this command line does is it reads that YAML file, talks to the API, and sees what's up and running. And it's saying, oh, I'm running Docker Compose stop, so I want to stop all my containers. So it looks at the Compose file, goes off to the API, and it sees that there are these 3 image of the day API components there's the image gallery, there's the access log, and it stops them all. Okay, now we've just got ordinary containers here. So if I do a docker container ls, I should see that there's nothing there because there's nothing running. But if I add the all flag, then I'll see that these image gallery containers, they're all still there. They're in a status of exited. So just as if I'd run the container and then the command had finished, or I could manually stop it with the docker container stop command, that would give me that output. And if I want to start them all again, then I do docker compose start. And that's the same as the docker container start command, which we saw in the episode about volumes, where we stopped a container, edited some data, edited a file inside the container file system, and started it again. It's the same container. While it's stopped, it's in the exited state. It doesn't use any compute resources. When you start that container again, either with docker commands or docker compose commands, it runs the entry point, or it runs the command instruction that's inside the Docker file that's part of the image, and it just starts it up again. So it's like a kind of reboot, effectively, with the current whatever state the container file system is in. So it started those things again. And if I now look at the container list, they should all be running. So yeah, they're all running, and we can see that if we have a look at this example here, this is my image of the day. It was created 4 minutes ago, but it's only been up for 36 seconds. So I can see that, it was created at this point, and then I stopped it, and then I started again 30 seconds ago. So you can see the life cycle is different, and you can stop and start containers. It's a really nice thing to do if you work in lots of different environments, or you work on different projects, and you want to be able to quickly switch from one to another. I can do docker compose up, work on my project. I get interrupted by something, I do a stop. The state of my application is all persisted in the container file system because it isn't removed. I've just stopped the containers. And then when I've dealt with whatever I'm dealing with, I do a docker compose start again. Everything's back the way it was. So I can stop and start different applications in different compose files, but not interrupt the flow of what I'm doing. Okay, so we've got that up and running. We've started individual containers, and that's all up and running. So when we do the start, it just lists through the services that it's working on. When we do the stop, it shows each individual container. And then when we go and look at those containers, we can see the individual container details. And we should see also in here, if you remember, when I looked at the definition for the API, I said the ports were I only specified the target port 80. And we can see here that this is being mapped to these random high-level ports. So if I want to go and look at a specific API, I can get a random port and go and browse to it. The reason I can't scale my containers up if I've got an explicit port mapping. So this is my UI component here, which is, let's just highlight just the one of them. My UI component in the compose file is specified to publish port 80 in the container to 8010 on the host. So any request comes into 8010 will go to that container. I can't scale up and run multiple containers from that spec because only one thing can listen on the port. I can only have one component listening on port 8010, which is not a container limitation. That's just a computer limitation. So if I want to be able to scale these things up and still access them from externally, I can specify just the target port, and then Docker will map it to a random port. Internally, it doesn't matter because this web UI component is talking to the API components on the target port. So containers can talk to each other over the network. You don't have to publish ports for container A to talk to container B. As long as it can reach it on the network via the container name, then it can access any ports that the container is listening on. Okay, cool. So I'm trying to keep these font sizes big, but it makes it a bit tricky to actually see what's going on. So I'm going to scroll down a little bit here. So there's a bunch more stuff you can do with Compose. So there's a little bit more of kind of walking around and playing around with it to see what you can do, but there's some really useful stuff in there. Start, stop, up, down, logs, to see all the things that are happening in there. You can also you can extend your specification in your Compose file to include things like the path to a Docker file, and then you can use Docker Compose to build a whole suite of container images, and we'll do that later on this week. Okay, cool. So now the thing you need to remember is Compose is a client-side tool. So even though I'm managing all these containers in a single tool, and I've got this nice YAML file that specifies my whole solution, I can't do anything without that YAML file. So as far as Docker is concerned, as far as the Docker engine is concerned, it's running my 3 containers or my 6 containers, but it doesn't know they're part of the same application. Only Docker Compose knows that they are part of one kind of coherent unit. And if I were to edit my Compose file, then it could get out of sync with what's currently running. So you need to bear that in mind. Your Compose file is your desired state. the engine itself doesn't know anything about what you're trying to achieve. They're just a bunch of containers, and Compose needs to have access to that YAML file in order to be able to manage them all. So you need to bear that in mind as you get to more used to using with Compose. And we've already done that. We've taken our app into a different state from what's specified in the Compose file, because I've scaled up the API component. Now, in the Docker Compose file, everything is spec to run on a single container, and I have like imperatively run Docker Compose scale to run more API containers. And what that means is my Compose file now does not reflect what's actually running. So if I can get myself into a tricky position there. So if I do a Docker Compose down, that's going to get rid of everything that's currently running. So my 3 API containers and the rest of my components are all going to be stopped. We'll see IOTD 1, 2, and 3, and then the image gallery and the access log. They all go through the stopping stage, and then eventually they'll come to the stop stage. Some of these take longer than others because when you stop a container, it gets a notification to close itself down gracefully. So it could be that I think the node application takes a little while to return and shut itself down correctly. When you do Docker Compose down, that's different from stop. Stop just stops the containers and leaves them there. Down just removes and clears everything down. So it stops the containers, it removes the containers, it removes the network if it created it. So it's like it never happened. It kind of undoes everything that it did. So now if I do Docker Compose up again, I'm not going to get back to the previous state that I was in, because it's only going to create one API container, because the YAML specification says one API, the scale of 1 for all my services. And Docker Compose doesn't know that I've manually scaled my application. So you need to bear this in mind if you're trying to manage it in 2 separate ways. So ideally, you'll make all the changes to your specs inside your YAML file, and you'll always do a Docker Compose up to bring your current state up to your desired state. So the YAML file, the Compose file, is the golden source of truth. If you've got your Compose file and you're also making changes like on the fly, then you don't know what the truth is going to be, because the truth is really still your Compose file. You've edited the running state of your application, and as soon as you go back to your Compose file for a new release, you'll lose any interim changes. So try and avoid that, and stick with the idea that this is my infrastructure as code. Effectively, I'm defining all the bits of my application in this one file, and when I make a change, I change the file and then bring everything back up again. And we'll see when I do this container list, I'm going to only have one API container, because that's all that Compose knows about. When I manually scaled the application, that didn't change the Compose file. Compose doesn't have any separate state. It doesn't have a database. All it has is the YAML file to go on. Okay, cool. So we've got all this up and running. We've got the app definition, which doesn't record scale. So that's all the stuff we've just talked about. So that's good. Okay, so yeah, this is the important thing. So when you deploy with Compose, it creates all those resources for you. The Docker engine doesn't know they're related. Yes, it knows there's a network and containers are plugged into that network, but it doesn't know that these number of containers are actually part of an application in itself. You can run any container and connect it to a network. It doesn't necessarily define the fact that they're part of a single logical entity. So you need to bear in mind that your Compose file is the thing that you need to manage your application, and that's got to come along with you. Like, you can't just log into a remote machine and manage the app. You need to have the Compose file as well. Okay, so we're going to come into a little bit of theory for a second here and look at the networking stack. Not at a low level. Don't worry, we're not going to go into some sort of a hardcore networking digression. But just to be clear about how these containers are managing to talk to each other without any complicated weird stuff going on inside the application themselves. So these applications have no notion that they're running in containers. There is no Docker SDK that lets you connect from one container to another. They just use the standard mechanisms that we've been using for decades. So when containers talk to each other, we got this here. Containers are plugged into each other on the same Docker network, and they can reach each other with their IP address. But of course, you don't use an IP address for connecting. You use a domain name, and Docker has its own domain name service built in. So anytime an application inside a container makes a DNS lookup, so when my web application makes a request to find out where the access log machine is, that request first of all comes to Docker's own DNS service that's running as part of the Docker engine. So first of all, it comes there. Docker says, "Is this name that you're asking for, is that a container that I know about?" And if so, I'll send you the container IP address. And if it isn't, because it's something like google.com or manning.com, then I will use the DNS lookup on the host machine that I'm using. So if you've got your own DNS server, you've got your own host name specified, they will come through from the DNS lookup. But if it's a container name, then Docker will return the resolution itself. So what you get then is apps just continue talking the same way. They're talking across the network. They're using domain names to communicate. And then you'll see this, the image gallery application, the web UI, it uses those different API components. And it just uses DNS to communicate. And we're going to go and connect to some containers here and have a look at how that looks. So I've got my application running with a single API container. I'm going to repeat that same scale command. So what this will do is it'll add 2 new API containers, and the end result will be I'll have 1 web container, 1 access log API container, and 3 image of the day API containers. And that's all super fast because containers. So they're all super fast to start and work with. Now I'm going to connect to that UI container. The way you do that is with the Docker container exec command. So exec runs a command inside a container, but you can pass it the IT flag, just like we did in episode 1 when we did Docker container run, which effectively means it's an interactive session. So this will execute a command inside a running container. So whatever process is currently running in the container will carry on running. So my web component will still be running, my web server will still be running, but I'll launch a new process, which is either a shell or a command session on Windows, depending on whether you're using Windows containers or Linux, and it will connect me to it. So I've got Linux containers today, so I'm going to do a Docker container exec. The name of the container, which I know will be this because Docker Compose builds that name using a standard format. IT to connect to it, and then shut to run my shell. So now I'm going to be connected inside my container. The web server process is still up and running. So I think, what did I use? 8010. So if I browse to this, I should still get a response from my container because it's still doing its thing. It's just started another process inside the container and connected me through into it. So if I go and have a look at, there are a couple of tools installed inside these images that I can use to do some kind of network debugging. If I go and do an NS lookup is just really lightweight tool that does a domain name lookup. So inside my web application and my image gallery application, if I do an NS lookup for the access log component, I get this weird error message, which is just an artifact of the version of Linux that this container is running inside. But I do get an address back. And that's the IP address of my container on the Docker network. So Docker networks are a nice way to kind of segregate workloads. So one container can only talk to another container if they're plugged into the same network, and that's because they have, they work on the IP addresses are bound within a specific network segment. So that's the IP address for my access log component. Anytime that my web UI tries to make a post request to http:/access log, it will get resolved to this container address by the Docker DNS server, and then it'll connect to that container. And it just happens to be the same container. Oh no, it's a different container IP address because they just random. So it's different from when I built this. It'll be different for you when you run this yourself. Okay, now the other interesting thing is if I what did I do here? If I get rid of that container, let's exit this and CLS. So I'm going to get rid of my container that I previously connected to. And even though Docker Compose is managing the application for me, it only manages it when I tell it to. So it's not like an orchestrator that when I start my application, it makes sure everything's up and running. Docker Compose just does what it's told. So even though I told it to bring up my application that included this image gallery UI component, if I go and kill the container, Docker Compose doesn't automatically recreate it for me. Docker Compose is not an orchestrator. It is just a way of managing kind of distributed applications where you still do the work yourself. So I've removed that. And if I now create a scale up again, I should need to scale up because I've already done this. Yeah, so they're all up to date. But because I did a Docker Compose up-d, I'm bringing a new access log container in there. So what I've done is I've removed my access log container. So that freed up the IP address that Docker had allocated, which was 21.0.2. And then I'm bringing the whole application back up again. So if this was Docker Swarm or Kubernetes, if I killed a component that's part of a wider solution, the orchestrator would recreate it for me. So Compose or Kubernetes Swarm or Kubernetes would create a replacement container for the one that I'd manually removed. because I'm just using Docker Compose, it doesn't have like a reconciliation loop that makes sure everything is what it's supposed to be like in a kind of constant loop. I manually do it. So I'm bringing the solution back up, so up, detached, and because I know that I've already specified the scale, I'm specifying that again to make sure that I've still got 3 instances of my API container. If I just ran Docker Compose up -d, I would lose those two API containers. So this gives me back up to the desired state. Okay, but with a new access log container. So if I repeat my command to go and shell into the UI, and I do another ns lookup access log, I may or may not get the same IP address as previously. So in this case, I have got the same one because Docker is quick enough to free up that IP address. And by the time I've recreated the container, it just uses the next free IP address, which is the same one as previously. If you were running this in a different environment, or there's on a Docker engine where there's lots of other things going on and people creating containers all the time, I would get a different IP address through. But the interesting thing that I want to show you here is if I do a lookup for the API component. So the domain name for this is the name of the service that was defined in the Docker Compose spec. So IOTD. That's what the configuration of the application uses by default when it's trying to get to the API. It uses that domain name. If I do an ns lookup IOTD, I get 3 responses back because I've got 3 containers running in that same Docker Compose service. So this is where the advantage comes in with Compose, that it lets you scale up your applications to multiple containers. What the DNS service does in Docker, if there are multiple instances of the container, it returns them all. So I see in my client, I see 6, 5, and 3, but it also randomly shuffles the response. So one of the problems with DNS is that historically it was quite expensive to use DNS to go and call a DNS server and get your resolution and get your IP address. So lots of client applications would cache that IP address like indefinitely potentially. Nowadays, DNS is so fast that ideally you don't want to cache it at all. You want to get the response because it's a mechanism that's used for load balancing. So what would happen here is the first time my application does a lookup for the API, it would get the response of 0.6 and it will make a call to that container. Next time it looks up, it might get 0.3. If the application doesn't understand about multiple responses, it will just take the first one. And because of that, Docker shuffles them around and you get some kind of basic load balancing that way. Like it's not proper, nicely balanced networking load balancing with like virtual IP addresses or anything like that, but it's a simple way to spread the load around when you do scale running on a single machine. So I get them in a different order, but I get all of them back. So depending on whether the client understands that or not, I would get either effective load balancing that the client can see, or I would get kind of a good enough load balancing for whatever environment I'm running in. Okay, cool. So DNS is the kind of core of how containers talk to each other. They just get an IP address and off they go. And again, because containers come and go, that's why you never use an IP address inside a container. I would never configure a specific IP address because when I kill that container to replace it with a new one, when I do an update or an operating system has a security patch that I want to roll out, the new containers will have new IP addresses. Like you will only get the same IP address as the container you just removed in a really static environment like this, where there's nothing else going on, and Docker is taking your container down, frees up the IP address, uses it again next time. Usually there's all sorts of things going on. You'll never get the same IP address, so you always work on domain names. Okay, cool. So that's the output that I've just seen in here. So we're gonna move on to another thing that I've touched on a couple of times, which Docker Compose really helps you with, which is this notion that your Docker images need to be portable. So they need to be packaged up with some kind of default configuration so that it's nice and easy. The developer workflow is nice and easy. People can do Docker container run or Docker Compose up, and the app starts and behaves in some kind of expected way, like in a dev configuration. But you also want to be able to pass configuration from the environment where you're running into your container. And we saw that with a few really simple examples when I did that web ping thing where I passed an environment variable, and the environment variable is what the application used to find out which address to go and query from, make an HTTP GET request, the interval for querying, all that sort of stuff. Environment variables are a really simple way. What we're going to see now is surfacing a file inside the container file system, which you've also seen when we looked at volumes. So in the episode about volumes, I surfaced a config.json file into my container. and that overrode the default configuration for the application. You can do all that stuff with Compose as well. So the to-do application, which you're going to load by the time you get to the end of the book, the default configuration is it uses a SQLite database. So a database file inside the container file system. So I just have one container running. It owns its own database inside the file. But it also has the ability to use an external database using Postgres. So I could run a Postgres container and connect the two together and have my data stored externally from my application container. So all the logic for that says, I can talk to Postgres. I just need some configuration to flip it one way or the other. That's all baked into the application image. It knows where to look for the config. And then you just supply the configuration that you want to when you run the application. And if we go and look at the updated Compose file for this, so inside here, I've got a Postgres version. Which one am I looking at here? This one here. And there are two services defined here. So remember, a service is just this abstraction over a container because it could be multiple containers. Doesn't have to be a web service or a REST service. It's just a naming convention for one or more containers. So I've got a database container here. This is running Postgres. Again, it's an image that I've got because the official Postgres image doesn't have a Windows variant. So I've got my own build. So if I run this on Linux, I'll get the official image. If I run it on Windows, I'll get an image that I've put together, but they all have the same image name. So I'm running a specific version of Postgres. I'm publishing the port. So maybe I'm a developer or a tester. I want to be able to talk to the database and query it to make sure the data's there as it should be. I'm plugging it into this network called AppNet. And then down here, let's scroll down. I've got my to-do web, my web application defined. Now this is a much bigger definition. A lot more stuff going on here, but this is what things look like as you get to a more realistic application that you're running in Docker. So it starts in the same way. I've got my image. That's my to-do list image, which runs that Noddy to-do application. I've got the port that I'm publishing. So again, the source port is 8030. That's the port this Docker's listening to on my host. It's going to send traffic into port 80 on the container. And then I've got an environment flag, and the environment variable says the database provider is going to be Postgres. That's an application-specific thing. So inside my application, I'm looking for that environment variable, and I'm saying the database provider is either going to be SQLite, which is the default if it's not presented, or I can also accept Postgres. So this is telling it to run in Postgres mode. It's gonna go and pick up configuration file to get the connection details for Postgres. So it depends on the to-do database because the database has to exist first, and it plugs into the same network, so it can find it using the domain name. So when I look at the connection details for the database, it will use to-do-db as the machine name for the database server. And then I've got this nice little thing in here, which is a secret. And the idea of a secret is you get secrets in Compose and in Swarm and in Kubernetes. They mean different things, but the goal is kind of the same. You're trying to express the fact that there's a configuration setting which contains sensitive data. So in this case, I've got a database connection string that's going to have a username and a password in there. And that's going to be sensitive. I don't necessarily want that being shared around. The mechanics of what a secret actually does depends on the platform you're using. So with Docker Compose, I can just use an ordinary plain text file, and it will say that the source of this secret is a secret called Postgres connection, and the target means that it will be presented inside the container file system at that path. So when the application runs in the container, it knows that it should be using Postgres because that's the environment setting. So the environment variable gets looked at first. And then it goes and looks in this directory. If it's using Postgres, it tries to find a file at /app/config/secrets.json, which will contain the connection string. Now, in Docker Swarm, that would be an official secret object, which is encrypted in the database. In Kubernetes, it would be a secret object, which is stored in the cluster database across all the machines. But it could be using, like a third-party secure encrypted storage unit to store the actual data. I'm just using a local machine with Docker Compose, so I don't have the advantages of a cluster database or a pluggable secret backend. So I've just got a file here, and what this does is it shows me that the secret that's defined as Postgres connection is coming from a local file. So in that file is config/secrets.json. So again, if I go and look at this inside here, this is the connection detail, and we'll see the server name is to-do-db. So that's the service name that's defined inside Docker Compose. That becomes the DNS lookup name for the container, and there are the sensitive things. So I've got my user ID in there and my password, So this is only any good for a development environment. But being able to specify it as a secret and having that kind of the model intact that says this is sensitive data. I'm in a test environment or a dev environment, so it doesn't matter. But in production, we should be using whatever secret provisions we have from our platform. Okay, cool. So when this runs, it will take the contents of this file on my host, and it will use a bind mount actually to present it at this location inside the container. When that's where the container is looking to get its connection details. So it's just a a nice way of using secrets in a way that makes sense and makes it clear what you're documenting inside your application spec. Behind the scenes, because I don't have a cluster, I don't have an encrypted data store. I'm just using a local file. Okay, so let's go and see how this looks when I run this through. So those are the things I've already covered. And this is the stuff I've covered too. So yeah, so secrets, anything that's sensitive. So API keys, you can put certificates in there, like TLS certificates can live inside a secret, connection strings, usernames, anything that might potentially be useful to someone trying to compromise your system. And that's the secret file that we've just looked at. Okay, cool. So let's go and run that, and we'll see how it looks. So if I go to to-do list Postgres, and again, I'm going to use everything's being managed with Docker Compose, so I need to be in the place where the Docker Compose file is. There's an alternative Docker Compose file if you're running on Windows, because these Compose files contain a file path. And that's one thing that is different between Linux and Windows on containers. So if I go and look at the Windows version of that Compose file, it's almost exactly the same apart from the target. So the target uses a directory, and it uses the Windows notation of backslashes instead of the Linux / notation. Now, most of Docker can work with / paths, and it will just sort them out for you. But with Compose, it kind of expects you to have a Windows file path if you've got Windows containers. So that's why if you're running on Windows containers rather than Linux containers, there's an alternative for you here. Okay, so we're in the right directory. I can just do a Docker Compose up-d. That's going to start up my components. So the other components are all already running. So my image of the day app, I haven't stopped that. It's still there. It's using some memory because those applications running in those container, those application processes will have allocated memory at almost 0 CPU because I'm not doing anything, but they're all still up and running. If I do a Docker Compose PS, what that will do is it will show me the containers that are running, but only the ones that I define within my Compose file. So it doesn't show me everything because there's a bunch of stuff there from other projects. Let's run that again. It only shows me the things that are defined in my Compose file. So I've got my to-do list Postgres to-do DB. So to-do list Postgres is the name of the folder, and Docker Compose appends that or prepends that at the start of the container name. Then there's the service name, which is to-do DB, which is my database, and then there's the instance name. So if I scale up, I would have, like I had my API, I had IOTD 1, 2, and 3. That's how Docker Compose builds the container names. And then I've also got my web application in there. It tells me what the command is running, how long it's been up, and any ports that are being published. So I've got my Postgres database, I've got my web application container, and the web application is configured to talk to Postgres, and it has access to the connection string, the connection details that are in that secret file, which isn't really secret, but could be in a different environment. Okay, so this is all up and running. A slightly longer chapter that should have said that at the beginning, but we'll still be done within the hour, I would think. Okay, so if I go and browse to this now, we're on port 8030 this time. So let's go and have a look at 8030. And I'll do the usual adding a quick task. So it's completely empty now because it's a new instance of the application. If I do let's grab one of these, finish episode 6. I can see that in there. If I go and look at the to-do list and refresh a few times, that's now being stored in Postgres. And I can test that with a Postgres database client. So this is a little tool from GitHub called SQL Electron, really lightweight SQL client that you can use for SQL Server and Postgres and MySQL and all sorts. Inside here, I've got the connection details for localhost port 5433 with the username and password. That's the wrong password actually, isn't it? So this should be Postgres as well. If I test that, it should connect to my container because I've published the port. And now if I save that and connect, I should be able to, it's connecting to my database. So even though it's a container, it's still a database that's running in there. You know from the previous episode that I could have a volume or a bind mount to have the actual physical data stored outside of the container. But inside here, it's just running in the container. This is the table, and that's the data that I've just put in. So it's stored outside of the container. It's the same container image that I've used previously, but by configuring it with my Docker Compose setup, I'm getting it to behave in a different way. So this would be like the test environment, as opposed to when I run it with SQLite, which I might use as a developer. So nice way of getting the application to behave differently, even though I'm using the same image. So if I had a problem with this in production, where I might be running with some remote Postgres server or a cloud database service, I could run the exact same image locally, but use SQLite and my little local database and replicate the issue there. Okay, so let's slim this down. Okay, so this is the thing here. So by separating the application package from the runtime configuration, we know that the deployment cycle for Docker is you build your image, it has a bunch of automated tests, and then you get an image with a version tag. You deploy that to whatever next set of environments you have. Like if you have some manual testing that needs to happen, you deploy the same image, the exact same binaries. When that gets approved, then you deploy the same thing to production. So you're promoting that same image all the way through. And then each environment is going to apply its own set of configs using whatever different mechanisms. But ultimately, you're going to be setting environment variables inside the container. You're going to be materializing files at specific paths where the application is looking for its configuration. And between all those different mechanisms, you can have apps that behave in completely different ways, but are using the same set of binaries in each environment. Okay, cool. So that's my to-do list. That's SQL Electron that I've seen in the screenshot in there. Okay, so the last thing to cover that I want to be clear of today is that Docker Compose, like as I said before, Docker Compose is not an orchestrator. It's not an alternative really for Kubernetes or Docker Swarm. The Docker Compose file format, the specification, is usable in other orchestrators. So like if you want to, if you get into Docker Swarm, which we'll do later, which we do next week, then the specification for defining your application is based on Docker Compose. So everything you learn about Compose, you can use that for Docker Swarm, which is the orchestration that's built into Docker. If you don't know what orchestration is, don't worry, we'll cover all that. Compose can also be used to deploy to Kubernetes. So I can take my Compose file and I can deploy and create a bunch of Kubernetes resources. But if I'm just using Docker Compose and the Docker Compose command line, I do not have the resilience of having multiple servers that can scale up and meet a lot of demand, or that can be reliable if a server goes down. I'm just managing a single Docker engine, but I'm managing it using a different command line. So it's a really useful part of your toolkit, and you will use Docker Compose. Like the usual workflow is I learn Docker, I learn Compose, and then I learn either Swarm or Kubernetes. And it's a nice kind of gradual learning path if you follow that example. Excuse me, I need to blow my nose. See, I told you it's live. Okay, so Compose lets you define your application and apply the definition to a single machine running Docker. That's the important thing. It doesn't give you resilience across multiple machines. It doesn't give you high availability. You kind of get the illusion of that because it has the desired state model, but you need to remember that it's always a single machine. And all it does is it compares what you've defined in your Compose file with what's currently running in that machine. So you need that Compose file to be able to manage your application, which is different from Swarm and Kubernetes because they have a database that lives inside the cluster. So when you deploy your application, I can manage it. I can deploy it from a YAML file, but I can manage it from any other machine without needing the YAML file because I can just see the resources inside the cluster. Compose doesn't have that. Okay, so that's probably all stuff that I've said in there. So this is this little diagram kind of shows you where these things fit in. So you will use Compose like for most of the life cycle until you get into the heavy environment. So you may very well use Compose. Developers will use Compose because it's a really nice way of running the whole stack of the application, or the majority of the stack, with a really lightweight set of containers. So, in production, I may be using a managed Postgres service. With Docker Compose, I can still use the exact same version of Postgres, but in a local container. I don't get the extra latency. I don't have to pay for a managed service. I can just get up and running really quickly. The CI process can use Docker Compose. You can automate all those things. So, all the Docker Compose commands you can have that as part of your build process. So you build all your Docker images, you do a Docker Compose up as part of your CI pipeline, and then you have your application running in containers, and you can run a whole bunch of unit tests, end-to-end tests, integration tests, whatever you like to get confidence that the changes of your application are good to go. Then in test environments, if you've just got small test environments, you can have single servers that are just running your application with Compose. If you don't need high availability, you don't need the resilience, then you can just run Compose on your servers. And then when you get to production and the pre-prod environments, then you'll probably switch to Swarm or Kubernetes. You can still base your definitions on your Docker Compose files, but you won't use Compose in production. Okay, so which as contradicting my last statement, that's not to say it isn't suitable for production, but it's not going to take you to cloud native, highly scalable, resilient application deployment in production. It is good if you're currently running VMs and you're looking at moving to Docker and you're replacing some of your VMs with Docker servers and you use Docker Compose. That's still a massive improvement on what you currently have, but it's not necessarily the end state. You're probably going to go from Compose to something else further down the line. But if all you've got at the moment is individual servers that you're managing in ways that are not easy to automate and not fast to make changes, then Compose and Docker will get you way beyond that. Okay, and so you know how this goes. There's the lab at the end. So all the exercises, they kind of tell you what to do and they tell you why things have happened. The lab at the end is for you to do a bit of exploration on your own. There's a goal here to run the to-do web application, to learn a little bit more about the Compose specification. So I said that the Compose doesn't restart containers for you, and by default it doesn't, but there are various flags in the specification that you can use to gain some more reliability for things like if the machine restarts, the containers restart for you. There's a few things for you to do there. And as always, you can find there's a link to the Compose spec where you'll learn a bit more about what you can do, and there's a link to a completed solution if you have trouble and you want to see how I did it. Okay, cool. So where are we? Let's switch back to which button do I press here? This one here. So that's about it for the chapter. We're at the top of time, and unfortunately, there are no questions that need. There's a question from Paul. So Paul says, how does Docker compare to Pogman? So Pogman is an alternative container runtime. So the container specification, there's OCI, the Open Container Initiative, that said this is what a container image looks like. This is what a container runtime should do, and there are different container runtimes. So Docker is the most popular, and Docker itself is built on top of this thing called Container D, which is a pluggable component you can take out. Podman is an alternative, and it's less well used as far as I've seen it, and it's certainly not as popular as Docker and Container D. Most containers that run in production are running on Container D because that's what Docker uses, and it's also what the latest versions of Kubernetes use. They use Container D directly. Docker puts a layer around Container D to add some kind of management features. Podman and there are other alternatives like Cryo and Rocket. They are alternative container runtimes which served a useful purpose of proving that the OCI was a spec that you could fulfill without Docker. But most of those have not carried on, had a huge following. So like Rocket has kind of gone into maintenance mode. Cryo has been in most places preferred for. Container D is preferred over Cryo. So in some environments, you will see these other container runtimes, and the bulk of the answer is you shouldn't really care. Some of them have alternative ways of running. So I think Podman is a daemonless service. You don't have a daemon that's running in the background. The containers kind of each have their own daemon, but it's not something I'm terribly familiar with. So the whole point of the OCI is that you can swap your runtime out, and you shouldn't really notice. But certainly in a development world, you're probably going to be using Docker because it adds the other components around the tools there. So I hope that was useful. Okay, so tomorrow we're back tomorrow, and tomorrow we're sticking with distributed applications. Part of the problem that you move to distributed applications, it gives you a whole bunch of extra abilities, so you can scale up really easily, you can move your applications around servers and all that sort of stuff, but you add these extra failure modes. So components need to talk to each other over the network, whether that's a physical network hop or a virtual network hop. There are lots of things that need to start up in the correct order and that sort of stuff. So you introduce potential new problems when you move to a distributed model, but Docker helps you with that. So tomorrow, episode 7, we're looking at supporting reliability with some other features in a Docker file called health checks, which is a Docker feature, and also dependency checks, so that your application, when it starts up, it knows whether it can do what it needs to do, and when it's running, it can tell Docker whether or not it's healthy. Okay, so that's tomorrow. That's episode 7, which is health checks and dependency checks. Today was all about an introduction to Docker Compose. Hope you found it useful, and I hope to see you again tomorrow. Thanks.